Welcome back. So this is going to be a continuation of the last section, right? I didn't have enough time to finish it, so we're going to finish it right now. Now, here we're looking for the probability of somebody who did not die of cancer, all right? And that was this probability here. Oh, nope, that'll erase it. All right, so I'm just going to leave it just like that. So somebody who did not die of cancer. So within the table, whoa, what happened? I don't know. Whoa, technical difficulties. Look at that. I think it dropped out of Zoom. There we are. And that should work out. All right, let's see. Here we go. Okay, so here we are. Now, we want to find the probability somebody did not die of cancer. So the cancer smokers was 200 out of the 1,000. So how many did not die of cancer must be the complement of that, which is 800. All right. Now, Part C, somebody who died of cancer and heart disease. Now, because this chart only lists the cause of death as only being subject to one of these cases, somebody could either die of cancer or heart disease or of something else, but not from both. Which means this probability is a mutually exclusive, comes from mutually exclusive events, which means the probability must be 0. Now, looking at Part D, somebody who died of heart disease or cancer. So if somebody died of heart disease or cancer, then we're going to be able to say, okay, let's use the formula that we discussed previously to say what's the probability of somebody that died of heart disease, that's 300 out of 1,000, plus the probability of somebody who died of cancer, that's 200 out of 1,000, minus the overlap. But remember, dying of heart disease or cancer was mutually exclusive, which means there was no overlap. So the probability in itself is just 500 over 1,000 to give us a probability of 50%. Part E, similar to what we just did in Part D. However, we do have the added remark here that we are looking at this particular probability here. This probability is the mutually exclusive probability. That means that these two are not disjoint. Therefore, these two probabilities do have an overlap, and they occur when one of the persons was a smoker and they also had heart disease. That probability comes down to 0.52, or in other words, 520 divided by 1,000. Now that we have more of a feel for probability, we want to go through and we want to start talking about these compound events. So, taking a little bit of time to read through these compound events, we want to go ahead and we want to establish what does it mean to have these compound events. And compound events just means that we're going to be combining. All right, that's basically what the word compounding means. So we're going to be combining one event to another. And we're going to use that using this little conjugation here, which is going to be and. So if we want to deal with a compound event, we're either going to be looking at an and statement, or we're going to be looking at an or statement. Now, very similar, when you saw a little while ago this whole probability of event A or event B taking place, we had a formula for that where we had to subtract out the probability where those two events were occurring together. Very similar, we're going to have to test whether these events are going to be dependent or independent. If events are independent, then we're going to have to calculate this one different way. And if the events are dependent, then we're going to have to calculate it a slightly different way. So let's look at these two examples down here. Within these two examples down below, we get this idea of event A. Let's say we find a parking spot. Event B, we'll say it's the first week of school. All right, so really quickly, let me backtrack on that. Event A, we're going to be rolling a die and getting a 4. Or event B, we're going to be flipping a coin and getting heads. Part B, we're going to be robbing a bank. Well, that sounds very bad. Or we're going to be going to jail. Okay, well, every item has an outcome. All right, so take some time and determine whether these events are independent or not. All right, and we're back. So on screen here, you have that the first example, rolling a die and getting a 4, and then flipping a coin, getting a heads. These two events are going to be independent. Now, why are they independent? Well, let's say I roll a die and I get a 4. Does that somehow affect the outcome of when I flip a coin, I will get heads? And the answer should be no, that the outcome does not depend on the previous one. Therefore, these two events must be independent. Now, part B. Let's say event C was robbing a bank and event D was going to jail. Bless you. Well, if you rob a bank, then more than likely you're going to be going to jail. Therefore, these two events are Therefore, these two events are dependent. Right? They're dependent on one another, and we're going to say that they are not independent at this time. All right. Now, next example, we want to find the probability of rolling a die and getting a 4, and then flipping a coin and getting heads. All right, so I want you to take some time and try to see if you can argue your way through this. See how we're going to find the probability of those two events. All right, and we're back. So, did you get the correct answer? Did you get 1/12, which is approximately 0.083? Now, my thought process behind this was that we need to find the probability that when we roll a die, we get a 4. Well, the 4 is just one number out of the 6 outcomes. And then flipping a coin, we want to make sure we get heads, but heads is only one outcome out of the 2. Therefore, when we want to find this probability of getting a 4 and flipping a coin and getting heads, it must be 1/12 according to the rules that we had right up here. Now, that's awesome. Second example. All right, I hope you tried the second example as well. Second example here says find the probability of drawing two cards from a standard deck of cards without replacement. And first drawing a queen of hearts and then a spade. So in order for us to look at the Queen of Hearts, we want to make sure that we want to select one card out of the 52, and then we're going to select the next card to be a spade. So in order for us to do this, we're going to do one out of the 52 cards. That card is going to be the Queen of Hearts. The next one that we're going to draw is going to be spades. Now, there are 13 spades. So that's going to be 13 out of the 52 cards. All right. Now, instead of saying 13 out of the 52 cards, we actually say it's 13 out of 51 cards because the previous card was actually taken out because this says without replacement. So as we multiply this together, we'll get some fraction that will be equal to 0.00490. And this will be the probability that we're looking for here. All right. Now, let's look at the next example here. So the next examples that we're going to be looking at here are as follows. We're going to be looking at a bag that contains assortment of Jolly Ranchers. There are 5 apple, 8 watermelon, 10 cherry, and 15 grape flavored candies. You can randomly select 3 candies without replacement. So what this means for without replacement, this means that we're going to select the candies, but we're not going to put them back. So when we select them, the initial sample size starts getting smaller. So let's go see if we can find that probability. So finding the probability that we get 3 grapes, or 3 grape flavored Jolly Ranchers. So the first probability we're going to look at, well, how many of these candies are grape flavored? And the first probability should be 15 out of the total. How many are there total? Well, we have to add 15 to 10 to 5 to 8. Getting that total, we should get about, what is that? Should be around 38. Yeah. So 15 out of 38. Now, after we select one of those 15, the next possibility is that we only have 14 grape Jolly Ranchers left out of 37, and that's all that we can select. The next probability is going to be that after we've selected the first 2 to be grapes, we only have 13 grapes left over out of the remaining 36. And when we multiply all of this, we should get an answer that's going to be approximated by 0.0539. Nice. So I hope you're following so far that this so far is what we're looking at when we're talking about when we're looking for probabilities that are dependent on one another. All right. The probability of choosing 3 grapes was completely dependent on us choosing the first 2 to be grapes as well. So we need to find the probability of not getting any apple Jolly Ranchers. So the probability that the 3 are not apple Jolly Ranchers. Not apples. All right. So how many apples are there? Or apple flavored? There should be 5. So we're going to subtract that 5 from the initial amount. So we should get that 33 out of the 38 candies are not apple Jolly Ranchers, and we can select one of them. If we select one of them, our next selection is going to be only 32 of the remaining candies. 32 are not apples out of the 37. We can select one. And then the last one, there's only 31 out of the remaining 36 that are not apple Jolly Ranchers. This now gives us a probability of 0.647. Awesome. Now that we have this idea that we get to work with how we're looking at these independent and dependent probabilities. As you can see in the previous example, those 2 probabilities were dependent on one another as soon as we wanted to take more than one candy within that selection. Now let's look at a different way of selecting where we're still going to get dependent or independent events. All right, so for this next part, we're going to be looking at the table given to us, and that table given to us is going to have that these certain amount of candidates, 35 of these candidates have a bachelor's degree, 15 of them have a master's degree. All right, so it says in the table is the highest level of education information for 50 applicants for a job. Part A. If 2 of these 50 applicants' names are chosen at random without replacement, so that means they're not going to put them back as soon as they select them, then what is the probability that the first selected has a bachelor's degree and the second has a master's degree? So we want one selection with a bachelor's, second selection with a master's degree. Probability that first is a bachelor's degree, and second, that they have a master's degree. So the first probability we're going to go through and we're going to see, okay, well, how many of the candidates have bachelor's degrees? And that's going to be 35 out of the 50 candidates. And then we're going to multiply this by the next selection. But again, we are doing this without replacement. All right, this is without replacement. That means that we're going to have a dependency here. Now, master's degrees. The second choice, we want them to have a master's degree, which will be 15 out of the 49. And I'll come back in a bit.